Greetings everyone, welcome back to multivariable calculus, and now we need to start focusing on extreme values of functions. You've done this kind of idea before, but the stakes are higher, of course, now because we have more variables involved, and there's a few other dimensions of depth, if you will, pun intended, on this particular topic. Since we have multiple directions to worry about, then you can have different combinations of things that may look like a max or a min or something like that, but it might not be the right combination. It might actually be a saddle point, or it might be some sort of weird wiggle in the graph. But the idea of this section is to treat this just like you did back in Calc 1. We're going to define places where extreme values can happen, and then I'm going to show you how we use the second derivative to categorize, or second derivatives, plural, to categorize these points so that we can be more precise, more sure about what each point is. So let's begin the same way you did in Calc 1. Let's define critical value, okay? Now, value is a loose usage of the word here because we're not plugging in a single value for a single variable anymore. When we say critical value, it's really a point from the domain. So if you have f of xy, then it's a point from the xy plane would be the critical value. Or if you have a function f of xyz, then it would be a point from 3 space, an x, y, and z coordinate point from 3 space, okay? No matter what, it's the same definition as back in Calc 1. A critical value is anywhere you should expect your derivatives to be 0 or undefined. But we need to be more specific now. It's anywhere the gradient at the point gives a 0 vector, or anywhere the gradient at the point is completely undefined, okay? Now that has two separate intentional meanings here. For the gradient at a point to be the 0 vector, notice the gradient can't be equal to 0 because the gradient is not a number, it's a vector, right? For it to be equal to the 0 vector, that's the vector with either 0, 0 if you're only 2-dimensional, or the vector with 0, 0, 0 if you're 3-dimensional, right? All of the partial derivatives at the point have to be equal to 0 for that to occur. They have to all be 0 simultaneously for that to happen, okay? Those are the ones that we typically get, the ones where the critical number is giving a gradient equal to the 0 vector. However, we also have the critical points where the gradient of the function can be undefined, and for a gradient to be undefined, you only need one of its components to be undefined, which means at least one of the partial derivatives at the point in question is undefined, okay? So for the first kind, all 3 have to be equal to 0 at the same time, or all 2 or all 3 or all however many partial derivatives you have, okay? Whereas with the undefined, it only takes one of them to be undefined to throw all of them out, okay, or to throw the whole gradient into being undefined. And just like in Calc 1, Fermat's theorem, but we're basically extending it, okay? Fermat's theorem basically said if you have an extreme value, like a local maximum or a local minimum, on some interval in Calc 1, this will be a region now, then that particular extreme value must be located at a critical point that is contained inside of the region that is continuous in, okay? So this is basically an extension of that theorem that was used in Calc 1, Fermat's theorem. Basically, it says all extreme values are critical points, but not all critical points are extreme values, right? See the difference? I can find tons of critical points. That doesn't always mean I'm going to find them to be a max or a min. Some of them could be saddle points. Some of them are critical and undefined, meaning maybe the function itself isn't defined, right? Sometimes that happens too at vertical asymptote or vertical, planar asymptotic surfaces, that kind of thing. So we just have to consider that if we find all of the critical points, we can find all of the possible extreme values. Okay? So now that we've talked about critical points, and I know you've used those before, let's take a look at a couple of functions here. I have a 2-variable function and I have a 3-variable function. Let's find the critical values, in other words, the points in their domains that cause either a gradient of 0 or a gradient to be undefined. Okay? Well, as you could probably guess, we're not going to find any of the undefines on these two, because look at them. They're nothing but polynomial, multiplication, whole number powers. All of these things are going to be smooth and continuous everywhere. There's no division by 0, no square roots and negatives, no crazy logarithms or anything like that. Okay? So these are going to be all smooth and continuous, but they may still have critical points where the gradient is equal to the 0 vector. So let's find out. So let's start off by computing the gradient. Remember, the gradient of the 2D function, right? The gradient of f here is going to be equal to the partial with respect to x, comma, the partial with respect to y. So that's what I'm going to compute first. The gradient of f here is going to be equal to 3x squared minus 3y. And for the other portion, for the y partial derivative, I'm going to have 3y squared minus 3x. So there's my gradient at any given point xy from the domain. Now what I want is the critical points. So what I'm going to do is set this equal to the 0 vector. And by doing that, what I'm really doing is setting each one of these equal to 0. But you got to keep in mind, I'm setting them equal to 0, but they're intertwined. They're working together. So just because I solve one of them doesn't mean I've found an answer. It means that I have to make sure and go back through both equations and find all of the solutions that work for both. Okay, so this is what I mean. I have 3x squared minus 3y equals 0. And since I'm doing the equals 0 kind, right, it's going to be an and. And 3y squared minus 3x equals 0. Okay, so doing a little adding and dividing, this one tells me that x squared is equal to y, and this one is telling me that y squared is equal to x. And I'm going to treat them like a system of equations. And I know you've heard that before. That's like substitution, elimination, all those things that you would have done back in algebra. Or if you took linear algebra, right, you would have done anything with the matrices and solving systems. Most of these are going to be nonlinear systems. Okay, so we're not going to do any of the fancy eliminations and things like that. Most of the time, we're going to fall back on substitution. And in this case, substitution is telling me that I'm going to be able to solve by plugging one of these into the other, right? So if I say y squared is equal to x, and well, actually, let's do it this way. X squared is equal to y, right? If I plug that into y, that's going to tell me that x squared squared, or x to the fourth, is equal to x. Okay? Now I hope on the side you're kind of seeing already, the only things that can square and give the other guy at the same time is going to be 0 and 1. -1 won't work on this one because they're not both squared in both equations. So if you try to do -1 in one of these, it'll eventually get rid of the negative and it won't work out. But let's go ahead and solve it. Okay? So I substituted the top equation into the bottom one. Now they're working together. And I got this equation as a result. So what I do is I move it, and then I'm going to factor this out. If I factor out an x, notice I'm going to get x cubed minus 1, which I can factor as a difference of cubes. Whoops. This one right here is telling me that x is equal to 0. This one right here is telling me that x can be equal to 1. This one has some imaginary values. Okay? And of course, we're not graphing in the imaginary realm right now. We're not dealing with complex numbers. So I'm just going to go with the 0 and the answer, 0 and 1 answers. Now, of course, that's not a complete answer. I found x equals 0 and x equals 1. I need to come back. We said that y is equal to x squared. Okay? So what this is telling me, when x is 0, y is equal to x squared. So then y is equal to 0. In other words, 0, 0 must be a critical point. Next, when x is 1, y is equal to x squared. So y is equal to 1 squared, which is 1. Therefore, I'm getting the point 1, 1. Okay? Both of these are critical points or critical values. You got to be careful with saying critical points because those two are not points on the surface of f of x, y. Those are points from the domain of f of x, y. I would then take the 0, 0 and plug it in and get 0, 0, 0. That would be a critical point because that's a point on the surface. Same thing here, right? If I plug in 1, 1, right, I would have 1 minus 3 plus 1, negative 1. So 1, 1, negative 1 is also a critical point. Whereas these are critical values because they're just elements from the domain. You could call them critical elements. We shy away from points unless you have the actual location of the thing on the object of the function itself. Okay? What about if I have a 3-variable function? It works no difference. Okay? Just because I can't graph this function because it's, say, 4-dimensional, doesn't mean that this kind of process doesn't make sense. It does actually make sense. What if I have this function representing the temperature energy in the room? I might want to find, hey, where's the highest temperature spot in the room? Where's the lowest temperature spot in the room? Well, if this represents the temperature of every spot in the room, x, y, z, I can still find critical values of this function, right? And then the critical values themselves would represent locations in the room. And then just because I can't graph the whole entire 4-dimensional shape doesn't mean I can't use level surfaces or something like that to try and understand the spread of the room better. Okay? So it still makes sense to optimize, to find critical values and things like that for 3-variable functions. Okay? You just have to treat it like I'm finding the maximum labeled object somewhere in 3 space or something like that. Let's go ahead and do this. The gradient of f here, don't forget now, this is a 3-variable function, right? So the gradient of f is going to be equal to the 3 vector, partial with respect to x, partial with respect to y, partial with respect to z. Okay, that's the gradient that I'm going to be doing here. Next, I'll find each piece. So the gradient of f is equal to the vector. So let's do with respect to x first. That would be this piece, and this piece. So I have z plus y minus 2. Next, the derivative with respect to y, partial with y only. That's these two pieces. I'm going to have negative z and x. I'll just put x minus z. And lastly, the derivative partial with respect to z. That's these two pieces. So I'll get x minus y. There's my gradient. As you can see, there's no square roots, no divisions by zero or anything like that. So I'm, again, not going to be worrying about the undefined kind of critical points. But I can find the ones where the gradient is equal to the zero vector. Just like before, I'm going to set each piece equal to zero, but with the thought in mind that these three equations must work together, not individual, to find, they're not finding separate critical points, okay, or critical values. They're finding all the same ones together. So right here, if I set this one equal to zero, then it's telling me that z plus y is equal to 2, right? Set this equal to 0, z plus y is equal to 2. Here, if this one's 0, that's telling me that x is equal to z. And here, this one's telling me that x is equal to y. Okay? And then these three equations have to work together in order for this to be equal to the zero vector. Well, x is equal to z and x is equal to y. So it looks to me like I could plug both of these equations back into this top guy right here and right here, which would then give me the equation x plus x equals 2, right? But that's just going to give me 2x equals 2, or in other words, x equals 1, right? But also, x was equal to z and x was equal to y. So if I come back over and plug this into both of those, I'm getting z equals 1 and y equals 1. Right? That's all of those equations working together, and that was the only solution that I found. It's actually just one solution. It's the point. Okay, I have my critical value is the point 1, 1, 1. Okay? So that particular point for this function might be a relative max or a relative min. It could be a saddle. It could be just some weird twitch in the graph that doesn't have any extra definition to it. More than likely, it's one of those first three, right? Either a saddle, a relative max, or relative min of some sort. Okay? So now, in the next scene, let's talk about how to categorize these critical values. Time to dig deeper into these problems and start actually categorizing the critical points either as relative maxes, relative mins, saddle, or something other, which could be inconclusive or just means that you couldn't categorize it and then you have to go look at a graph to get a better inspection, which does happen. But hopefully this process is something that you can, get used to doing quickly, and it helps you categorize most of the critical points that we come across. So first what we need to talk about is the Hessian. The Hessian is a matrix that we make to organize the second partial derivatives of a function. And technically, you've been creating a 1-by-1 Hessian ever since Calc 1, because the Hessian of a normal f of x function is the second derivative fxx of that function. Okay? So then, as you gain more variables, you have more partial derivatives to combine. Okay? So the Hessian of a two-variable function, f of xy, is the double partial of f with respect to x, then fxy, which is the partial of x, then the partial of y, then down here f is the partial of y, then x. And remember, for continuous functions, or at least functions that are continuous at the point where you're investigating, those two values are going to be equal anyway, right? Because that's linked to continuity. And then, of course, f double derivative with respect to y partial in both directions. So you can see it's what it is a matrix that's just organized all of your second partial derivatives. So it kind of acts like your second derivative tester. Okay, the matrix has all of the second derivative information in it. It just has to be analyzed appropriately. So organizing it in a fashion does help you remember how to do it and to be efficient in going through it quickly. Of course, if you have a function of 3 variables, it's the same idea, right? You do all of your x partials first, then you have x, y, and z partials as your second. Do all of your y partials, then second partial x, second partial y, second partial z, so on and so on. And this doesn't have to stop at 3 variables. You can have a function of any size number of variables, and then of course that would determine the size of your Hessian matrix, right? For the examples we'll be doing here, I will be doing 2 variable functions and 3 variable functions. So you'll see this 2 by 2 type of Hessian or a 3 by 3 type of Hessian, okay? Now, once you've created your Hessian matrix, we organize the data of the determinants of the square pieces inside of the matrix. And depending on the size you have is how far you have to go with what I call these D values, okay? D1 is always going to be the double derivative of x with respect to x of the function f. So you'll notice that what that is just the top corner of each one of these, right? And in the case of your Calc 1 variable functions, you would stop at D1. That would be your, your second derivative, in which case you would be doing your second derivative test like you always have. And, whether it's positive or negative tells you if you have a maximum or minimum. This feeds directly into that, and that feeds from this too, okay? D2, what it is you're going to multiply the double x and the double y partial derivative minus the cross derivatives multiplied. In other words, and these are the same, so really it's just squared. But if you look a little closer, what this is the determinant of this 2 by 2 matrix. It's fxx times fyy minus fyx times fxy. So it's this diagonal minus this diagonal. That's the determinant of a 2 by 2 matrix. Okay? So D2 is the determinant of the 2 by 2. D1 technically is the determinant of the 1 by 1 fxx. If it's one element, the determinant is that element. So what do you think D3 is? The determinant of the 3 by 3. And if you had 4 variables, D4 would be the determinant of a 4 by 4, and so on and so on. Okay? So what do we do with these determinant values? Well, organizing these determinant values in different combinations will tell you, as you plug in the points, mind you, okay? You're going to want to do these determinants, but also before you've even gotten here, hopefully you've already identified the critical values, and you'll be plugging the critical values into these determinants, into these Hessian matrices, so that they won't always be so generic and they won't be so bulky, okay? But I mean, you can do it wherever you choose, but at some point, pun intended, you're going to be plugging in the critical values, because those are the ones we're investigating with these matrices anyway, okay? And once you do plug them in, the different combinations of these determinant values will tell you if that particular critical value happens to be a relative max, a relative min, a saddle point, so on and so on. Okay? So you do your determinants and you've plugged in your point. If your determinant number 1 is positive and determinant number 2 is positive, you've got a relative minimum. Okay? Now notice the only thing that changes here is determinant 1. Determinant 2 being positive is linked to you having some sort of relative extreme point. Notice that. D2 is going to be positive if you've got some sort of extreme point. But D1 being positive or negative is what's going to control whether it's a min or a max. Okay? So your D1 being negative would tell you that you have a relative max, as long as your 2 by 2 determinant is positive. Okay? Anytime your 2 by 2 determinant is negative and everything else is defined normally, you've got a saddle point. Okay? And then any other combinations where, like, say, D2 equals 0 and things like that, it's going to be inconclusive. And all that means is this particular method isn't enough. You would probably need to go sample it graphically if you can, or you may even have to step up and use technology to evaluate your function. Doesn't happen as often, but I mean, there are cases where it can happen. So, okay. And then also the same ideas go for the 3 by 3. Okay, you've just got 3 determinants to look at. Okay, I want you to see how the 3 by 3 has the same cutout of circumstances. It's just basically a broadened cutout of the 2 by 2. Okay, so notice D1 being positive and negative can tell you if you have a min or max. D2 is always positive if you have an extreme value, but D3 follows the same mode as D1. The 3 by 3 determinant will be negative if you have the relative max, along with D1 being negative if you have the max. They'll all be positive if you've got the min. Now, as long as D3 is not 0 and you have some other combination of the other 2 determinants, that's going to indicate that you have a saddle point. Okay? And then everything else that's inconclusive would be like where D3 is equal to 0 and you have other weird combos of things maybe being undefined or whatever. Then inconclusive, it just means that, you have to go analyze it otherwise. Okay? All right, so let's take this idea here and let's actually apply it. By the way, if you're wondering about the positives and negatives on these, you would have to go probably to an advanced calculus textbook and investigate the proof for yourself. It's based on linear algebra, and it has to do with the way determinants are formed on top of the way these derivatives interact with each other. So let's apply these here to these 2 functions that we've already done the gradients and found the critical values for, right? Now let's categorize those critical values. So here's the function, here's its gradient. Next, I would want to create its Hessian, right? So this is a 2-variable function, so I will be creating this type of Hessian right here. So the Hessian of f, right, in this case, is going to be the determinant. So I have to do the double x, right? Well, look, these are my partial derivatives right here already. I'm just going to do the derivatives of these and feed them into the matrix here. So this is already fx right here, right? This piece right here is already the partial derivative with respect to x, and this one is already the partial derivative with respect to y. So to do the double x derivative, I'm just going to take another derivative with respect to x here. That's going to be 6x. Next, to do fxy, I'll do the y derivative of this guy right here. That's -3. Next, to do yx, I'll do the x derivative of fy. That's -3. And lastly, to do the double y, I'll do the y derivative of fy, which is going to give me 6y right here. Okay. Now, as you may notice, this particular Hessian is based on some values of x and y. So it does matter if I plug in the critical values here. I will have different Hessian measurements, different matrix measurements at different points. Some functions don't, some functions do. Okay, this one does. So what I need to do is set up a Hessian for each one of those critical points. Okay, so here we go. The first critical point was 0, 0, right? So at 0, 0, my Hessian is going to be equal to the matrix 0, -3, -3, 0. So then if I do my 2 determinants, right, D1 is just the corner, right? So D1 in this case is 0. D2 is going to be 0 minus positive 9. So I'm getting negative 9. All right, well, which case is that? We're getting the case where D2 is less than 0. So this piece right here tells me that this is a saddle point. Okay, so in the function fxy, the point at 0, 0 is a critical value. It's flattened out, right? Has a 0 vector derivative, a 0 vector gradient, but it's a saddle point. Okay, now let's do the other critical value. The critical value at 1, 1. My Hessian for this point is going to be 6, negative 3, negative 3, 6, like so. And if I set up my determinants, D1 is going to be 6, D2 is going to be 36 minus 9, so that would be 27. And D1 and D2 are both positive, right? So this is telling me right here that this is a relative minimum. Alrighty? Okay. Next, let's do the three variable function here. For f, x, y, z, right? I've got my gradient right here. Let's go ahead and set up the Hessian for this matrix, for this function, the Hessian matrix for this function. That's going to be x derivative. Notice there are no x's here, so I'm getting 0. Next, it would be the y derivative of this one. That would be 1. Then the z derivative. That would also be 1. Okay, next row. The y x derivative. So here's the y component, right? Do the x derivative. That's going to be 1. Then do the y derivative. That's 0. Then do the z derivative. That's negative 1. Next row, z component, x derivative is 1, y derivative is negative 1, z derivative is 0. Notice this particular Hessian does not depend on the location in space. That doesn't mean anything in particular. Okay, it just means that the measurement using your second derivatives is going to be the same everywhere. You could very well still have maxes and mins or saddles. They're all still possible. Okay, it just means that it doesn't vary throughout the space that you're measuring. Okay, so we only had one critical value this time. We had 1, 1, 1. Okay, so I would say, at 1, 1, 1 like this, but I'm not plugging in anything, so it doesn't matter. And what I'll be doing is taking the D determinants here, okay? But D1 and D2 are straightforward, obvious. D1, right, is 0. D2, if you just sort of look at it like this, like you block out, D2 is this determinant here, which would be 0 minus 1. So D2 is negative 1. D3 is the determinant of the whole thing. Okay, so we'll go ahead and just do it by the cofactors here. I've got the cofactor 0, and then I've got to do this little determinant down here. That's 0 minus 1. So 0 times 0 minus 1. Next element is 1, but I've got to do minus because they alternate. So minus 1 times. That would be this determinant here where you block out the row and column. That would be 1 times 0, 0, minus negative 1, right? So plus 1, because it would be this 1 times that negative 1. And then last one would be plus the one element here times the determinant of this little piece here, because I'm blocking out this row and column, that's going to be -1 minus 0. Okay, so this is 0 and it's gone. This is going to be -1. This is also going to be -1. So I'm getting that D3 in this case is -2. So looking at my different cases here, right? This is a combination where D1 is 0 and D3 is negative, D2 is negative, so obviously it's not going to be one of these. But D3 is not 0, right? So all three of these put together tell me that this is a saddle point. Okay? Now what that looks like in 4 dimensions, you know, is up to the imagination, of course. You would have to do some serious, you know, extra graphing to get a 4-dimensional shape saddle point out there. But that doesn't mean that we can't still use this to help us when we're using this function for something in 3 space, right? Who knows what this could actually measure at every point in space. And all this is telling me is I do have a point where all of the derivatives slow down, but they don't actually form a maximum or minimum value. They slow down and have sort of a swooshy saddle point there, okay? Let's take a look at those 2 functions that we were just doing the critical values of, and then subsequently also doing the Hessian and identifying them. Now that we've done both of those, we've found the critical values and we've identified what kind they are, let's see what that looks like. So we had the function where z is equal to x cubed minus 3xy plus y cubed, and that happens to look like this. Notice it has a very sheet-like nature, except for when you get right here into this middle section. And notice we have that saddle point right there at 0, 0, 0. Right? And then also, you can see that we have that minimum value that we located, and it's exactly at 1, 1. Right here is that minimum point right here. Right? You can see that it's happening right there at the crosshairs of those 2 pieces right here. So that's definitely the saddle point here, and then the minimum point here that we calculated. Next, the other one that we identified was a 3-variable function. So the best I can do for you here is to graph several of the level curves. So what you need to remember is that what I'm showing you is not the full graph. It is a slice from 4 dimensions into this 3-dimensional figure. Okay? And then of course the important point that we found was the point 1, 1, 1. And what I want you to notice is if I plug in 1, 1, 1 for x, y, and z, I get a w value of -1. So what you'll see is I'm going to change the w value constantly. And when it hits -1, something special will happen. Okay, so here's one level surface. This is one slice from 4 dimensions into our 3-dimensional space. You'll notice what it is a hyperboloid of 2 sheets. As I let w progress more positively, what you'll notice is that the hyperboloid of 2 sheets, they'll start approaching each other. So let's go. Right, so as w increases, notice, see the 2 hyperboloid sheets are approaching each other. Okay, now we're getting close to -1, and right there at -1, notice that's the point to where when I'm slicing into the level surfaces, the 2 actual pieces of the hyperboloid of 2 sheets have now met and created a cone, an actual cone instead of a hyperboloid of 2 sheets. And then as it progresses past this, you'll notice it becomes a hyperboloid of 1 sheet, and you can actually see through this now where they've met up and reached around each other. Okay, so -1 was a very important value for this particular function. It happens to be a saddle point because of the way the different dimensions are changing in opposite ways, right? The 2 points right here are approaching each other, but w is increasing, okay? So you're getting a point where all of your derivatives are flattening out and not changing as much when they get to this w value. But then they quickly begin to increase again and get us into a realm where we have this hyperboloid of 1 sheet. Okay? Now let's work some examples from beginning to end in finding the critical points and then classifying them. Okay? So here we go. E to the negative x squared minus y squared. And I know if you've watched the previous lecture, you've already seen, we've talked about the gradient of this one and the partial derivatives on this one, right? The gradient of p here is going to be equal to the vector where, remember, doing the exponential derivative gives itself, right? And then each one of these chain rules is going to be one or the other. Since one of them's held constant, we'll go to 0. I'm going to be left with negative 2x e to the negative x squared minus y squared, and negative 2y e to the negative x squared minus y squared, like so. All right, from here, I'm going to look for critical values, but I'm going to notice right away that I don't have any divisions by zeros or square roots or anything like that. So I'm not looking for any of the undefined kind of critical points. All right, so I'm going to set these equal to 0. Negative 2x e to the negative x squared minus y squared equals 0. And negative 2y e to the negative x squared minus y squared equals 0. So then from here, don't forget that an exponential by itself is never going to equal 0. There are no values of exponents that can cause that. So the only solution I'm getting from this one is x equals 0. And same thing over here, I'm only getting y equals 0. And remember, both of these things have to be 0 at the same time. The only way that's going to happen is if both of these values happen simultaneously. So my critical value is the point 0, 0. Right? If you remember the image of this from the last one, you'll know that we're staring at the peak of the hill on this one, right? Okay. So now we need to set up the Hessian of P. So I'm going to take my x derivative here, and I'm going to take the x derivative of it, which is going to be a product rule. So I'm going to have negative 2 e to the negative x squared minus y squared, then minus, plus 4x squared times the same thing. So I'm just going to factor it out. Plus 4x squared e to the negative x squared minus y squared. Double check with me. I took the derivative of the 2x portion of the product rule, right? Left the exponential alone. Next, I kept the negative 2x and did the derivative of the exponential portion, which kept itself again, and then popped out another chain rule, negative 2x, and the negative 2x times the negative 2x gave me 4x squared. Okay, so then the next point will be the y derivative of this guy right here. And there are no y's multiplied, it's just the y up in here. So I'm going to end up with a negative 2y chain rule, which is going to give me 4xy e to the negative x squared minus y squared. And of course, the continuous derivative here is going to be the same, right? My second crossover partials is going to be the same there because it is continuous at 0, 0. And then I'm going to do my y derivative here, which is going to be very similar to doing the x derivative on the x portion here. So I'm getting negative 2 plus 4y squared e to the negative x squared minus y squared. Okay? Now, of course, I'm only interested in the point 0, 0, in which case e to the 0 power is just going to give me 1, and then 4 times 0 here, 4 times 0 here, 4 times 0, 4 times 0 wipes out both of these, and I'm left with the Hessian matrix at 0, 0, the Hessian of P at 0, 0 is equal to negative 2, 0, 0, negative 2, like this. Okay, so notice my D1 being just the top corner here, the fxx is negative, and then D2 is going to be the determinant for minus 0, so 4. And remember, when D1 was negative, D2 was positive. D2 being positive means you have maybe an extreme value. D1 being negative means it had to be a maximum. So with these two pieces right here, I can say that I have a relative max at 0, 0. And if you remember the graph, and I'll show you again after this scene, you remember that it's just that hill, kind of like a probability function, and it is indeed a maximum point at the top of the hill there. Okay? Now, let's talk about the function fxy equals 5x over x squared plus y squared plus 1. Okay? So we have a few quotient rules to dish out here. Let's go ahead and get all of those out of the way. Okay? So I'm going to do the partial derivative of f with respect to x. So that's a low d high. That's going to be 5 x squared y squared 1 minus high d low. And it's derivative with respect to x. So it's just going to be 2x times 5x. So 10x squared over square of below. So x squared, y squared, 1 squared, right? Okay. So my gradient of f, first component, is going to be negative 5x squared plus 5y squared plus 5 over x squared plus y squared plus 1 squared. Right? All right. Now the fy partial is a little bit cleaner. There's no y's in the numerator. So I'm going to have 0 times that piece, or you could have done it with a negative exponent. And then minus, I've got the 5x times 2y from the bottom. And then, of course, the denominator squared, right? So I'm ending up with negative 10xy over x squared plus y squared plus 1 squared. And there's my gradient for this guy. Okay? All right, so now let's find our critical points. We've already done these calculations, so let's make some space here. And I'm going to set these, well, let's check it real quick. We have a denominator, right? X squared plus y squared plus 1 can't be 0, which of course that's true in the original function as well. But you'll notice x squared plus y squared plus 1 is never going to be 0. But even if it was, those would be points that would be excluded from the domain since they're in the original function too. Okay? So obviously if they're excluded from the domain, you're not going to be able to do a derivative, much less a gradient at those points anyway. Right? Which means they would be critical values, of course, because the derivative would be undefined, but more than likely not good ones for us. But x squared plus y squared plus 1 is never equal to 0, so no worries. I'm not going to have any of the undefined kind of critical values here. I'm just going to be looking for the equals 0 kind. More good news. If I have a fraction equal to 0, that only happens when the numerator is equal to 0, right? So the two equations that I'm looking at here to solve are going to be negative 5x squared plus 5y squared plus 5 equals 0. And, right, together in a system, negative 10 times x times y is equal to 0. Remember, they have to work together to find the critical values. They can't do this independently. The bottom equation is very easy to solve. We have, from this bottom equation, either x is 0 or y is 0. Okay? Now, those aren't solutions yet because we don't know what happens when we apply this information to the other equation. Okay? So when x is 0, let's go ahead and split this up here. When x is 0, the top equation becomes 5y squared plus 5 equals 0. I think you'll quickly see that this has imaginary answers, right? Just from a subtraction and a division and the square root. However, when y is 0, I get the equation negative 5x squared plus 5 equals 0. And then that tells me x squared is equal to positive 1, which of course has the two solutions. X is plus or minus 1, right? I then apply that back to the point in question here, and I've located some critical values, right? So my critical values are going to be the points 1, 0, and negative 1, 0. Does that mean I have one max and one min? Does it mean that they're both saddles? None of that means anything yet. I have to investigate each of those points now with the Hessian, right? Okay, so next, we got more derivatives to do, right, of these lovely beasts. So here we go. I'm gonna set up my Hessian here, right? My lovely, lovely Hessian. I'll work over here and feed it into over here, okay? So I'm doing the fxx derivative here, which means I'm going to do a quotient rule of this beast right here, okay? So low d high is going to be x squared plus y squared plus 1 squared. D high is going to be negative 10x minus high d low. So minus negative 5x squared plus 5y squared plus 5. And d low, ooh, yummy. I didn't give myself enough space. Hang on, I'm going to show you a trick that's going to shorten this right here. Okay, so low d high, x squared plus y squared plus 1 squared minus 10x minus negative 5x squared plus 5y squared plus 5. D low is 2 x squared plus y squared plus 1 times 2x. Okay, and square of below gives me x squared plus y squared plus 1 to the 4th. All right, so let's get rid of the obvious. I can get rid of one of these from each. So that makes this 2 a 1, and it makes this 4 a 3. Right? Okay. Now, of course, I could sit here and multiply all of this stuff out and try to make sense of all of those pieces. I think instead what I'm going to do is set up a Hessian for each of those points. And all I need to do is plug the points in to this, because even though this, isn't simplified, it still is going to have the same value. Okay, so here I go. At the point 1, 0, my Hessian is going to be equal to, and we're going to put some values in now. Okay, so x is 1, y is 0. X is 1, y is 0. Okay, so I've got 1 plus 1 is 2 times negative 10 is negative 20. Negative 20. And then I've got right here, x is 1, y is 0, and x is 1. So that's negative 5 plus 5 is 0. So that wipes out that whole side for that one when x is 1. That's going to also happen when x is negative 1. Isn't that cool? Yeah. Okay. So then I'm left with negative 20 for the numerator because this piece was 0. In the denominator, I'm going to have 2 squared. I'm sorry, 1 squared is 1. 0. 2, right? Negative 20 over 2. I'm getting negative 2 cubed is 8. Right? I forgot the cube is still on that one. I wasn't on that one anymore. Okay, so I'm getting negative 20 over 8. Let's see, that'll be negative 5 over 2. Okay. At negative 1, 0, my Hessian is going to be equal to, all right, let's do this again. When x is negative 1, right, and y is 0, I'm still getting 0 for this piece, which is going to wipe out that whole side. And I'm still getting 1 plus 1 is 2, right? And I'm still getting 2 cubed. So I'm actually getting the same value here, negative 5 over 2 right there. Let's double check now. Oh, no, I'm not. I'm getting positive because it's negative 10 times negative 1, right? So that gives me the positive. All right, now we're cooking. Good deal. The crossover derivative, fxy and fyx, is going to be the same for both, right? It would probably be easier to do the x derivative of the y component rather than the y derivative of the x component. Okay? Okay, so I'm going to do the x derivative of this piece right here, which is going to give me low d high is negative 10y, and then I have x squared plus y squared plus 1 squared, minus high, so plus 10xy, d low, right? So that's times 2. That's going to give me 20 right here. X squared plus y squared plus 1. Inside derivative is 2x times 2x. And square of below, x squared plus y squared plus 1 to the 4th. Just like last time, we'll reduce what we can immediately. This piece will go away with one of these and one of these, right? So that's to the 1 power, that's to the 3 power. And what we're going to do is we're going to get, both of these components here because they're going to be equal. All right, so at 1, 0, this times y, right? So I'm getting 0. Here also times y, right? So that's getting 0 wiped out. Make sure the bottom doesn't, right? It's not. I'm getting 8 in the bottom again. So I'm getting 0 for both of these. And then notice y is still 0 for this one, so I'm actually getting 0 for both of these as well. All right, last tidbit. The fyy derivative the y derivative of that piece up there, I will get negative 10x for the d high, x squared plus y squared plus 1 squared. And then high d low, so plus 10xy. The derivative of the low drops a 2, x squared plus y squared plus 1. And then the inside derivative would be another 2y. Okay. And then square of low, right? X squared plus y squared plus 1 to the 4th. Let's wipe out what we can. This is going to be a 3. This is going to be a 1. And then this piece is gone, right? Okay. I'm plugging in 1, 0. Notice this is multiplication by y. That's going to go away for both of them. So this whole piece right here is going to not contribute to these particular points. My denominator is the same as it always has been, right? I'm getting 1 plus 1 for both of those two. Both of my denominators are going to be 8. For this guy right here, though, I'm getting a times 2. Actually, it's going to be times 2 for both of them, right? So really what I'm getting is a negative 10x over 4 for both. And 10 over 4 reduces to 5 over 2. So then it's really up to the x, right? I'm getting the negative 5 over 2 here and positive 5 over 2 here. Alrighty. So D1 is negative 5 over 2. D2 here is 25 over 4 minus 0. 25 over 4. Over here, D1 is 5 over 2, and D2 is, again, the 25 over 4, right? They're very, very close to being the same, but not quite, right? Because this one is negative and this one is positive right here, right? Negative, positive. This is a relative max. And this one is positive and positive, so I've got a relative min. Okay? So I found two critical values, right? This one's going to be a hill, right, with a maximum point. This one's going to be a trough, a minimum point inside of this really curvy surface. Okay? Now this is the calculus side. Go look at the GeoGebra so that you can see exactly what these look like and you can tell that these things are actually correct. And just a quick look at these two functions that we were finding the critical values of and classifying them. Z equals e to the negative x squared minus y squared is this one. If you remember from a previous lecture, we talked about how this looks like a generic form of a bell curve. It's like a three-dimensional bell curve almost. Like has this little pocket of probability right here in the center. But the main point is we calculated there to be a maximum at 0, 0. And from the xy plane, you'll notice 0, 0 is right here on the z-axis. And it is indeed the very top peak of this hill right here. So it is the maximum value actually of the entire function. It ends up being an absolute maximum of the entire function, whereas the rest of the function is asymptotically trying to approach the xy plane. Okay, the next one, let's zoom out a little for the next one. The next one we found two critical values for. I'll zoom back in a little to get a little bit more detail on those. Okay, so notice that I've got a peak right here and a valley, a trough at this point right here. And you'll notice that notice the red axis, of course, is the x, the green axis is the y, and this peak is happening right at 1, 0, and the trough bottom is happening at negative 1, 0. Right? Just as we calculated in the video. we have the maximum at 1, 0 and a minimum at negative 1, 0 here on this guy. Let's finish up with one more example of a 3-variable function. I have gamma of xyz is equal to the ln of x squared times y squared times z squared minus x plus y plus z quantity. Okay? Seems pretty out there, right? Don't forget your laws of logarithms. Before I even do any calculus here, I'm going to split this one up. I'll have 2 ln of x plus 2 ln of y plus 2 ln of z, right? The multiplications allow me to split them with additions. And then, of course, then their individual exponents I can bring out. And then I'm going to distribute the negative here, like so. All right. So now the gradient of gamma is going to be equal to, well, the derivative of the ln x, right? That's just going to be 2 over x minus 1. Same thing for y, same thing for z. So I have 2 over y minus 1, 2 over z minus 1, like so. Okay, and then for each of these, remember, I'm trying to find the critical values. Individually, by themselves, they can be undefined. Notice right here, x can't be 0, y can't be 0, also z cannot be 0. That was already self-evident from the original function, though, because of the original function here, the domain is all points in xyz space except when x is 0, when y is 0, when z is 0. Because they're multiplied, any one of them being 0 would zero out the whole thing. And remember, the ln of 0 is undefined, has a limit going to negative infinity. Okay, so that's the only point left out, though, because the squares that are in the original function take care of any negatives, right? So when we do this, actually, when we do this trade over, we technically should have the absolute values on each of those. It's not going to affect us, though, because we're still using this as our original function. Okay, so the domain is all of 3 space except the point. All of 3 space except for the axes themselves, which is evident here. Remember, it only takes one of these to be undefined to make the whole gradient undefined. So just by itself, x being 0, right? That's an entire plane, right? I said axis, I meant plane. Y can't be 0. That's an entire differently plane, right? Z can't be 0. Yet another different whole plane out of the domain. Okay? So we can't be on any of the trace planes for this particular function. It's going to just exist inside of the octants themselves. Also, though, let's list that under critical values. Right? So far, critical values, I have x equals 0, which is an entire set. Y equals 0. Z equals 0. Each of these are planes full of points that are all critical values, right? These are all planes of critical values. They're not going to be that useful, though. They are the undefined kind, but they're not the good kind of undefined kind. They're not the kind that end in like cusps or anything like that. These are the kind that are leading this logarithm to be a negative infinity type of thing, right? Vertical asymptote type of thing. These aren't going to be fun at all as far as optimizing and finding max min points, okay? So then what else is there? Well, I can set each one equal to 0, all right? And notice they're all going to solve the same way. If I set this equal to 0, right, I can just add the 1. And what x value do you think is going to give us a 1 here, right? That's going to be x equals 2. All of them are going to solve the same way. So the other critical value that I'm finding is the point 2, 2, 2. Okay? So I have these planes, x equals 0, y equals 0, and z equals 0. Those are all sets of critical values. But then I have the individual critical value 2, 2, 2. And this is the equals 0 kind, equals 0 gradient vector. Okay? That's going to be the fun one. All right, so let's do our Hessian matrix. The Hessian of gamma is going to be, okay, so from my x component here, I do the x derivative, which is going to give me negative 2 over x squared. There are no y or z's in the x component, so the y derivative and the z derivative are both 0. The same thing happens with all of the other components. I'm going to have 0 in the off diagonal components there of the second derivatives. The y derivative is going to be the negative 2 over y squared. The z second derivative is going to be negative 2 over z squared. And notice now, even though these are critical values, right, I should still check them, even though they're the undefined type, right? But notice the Hessian will also be undefined at either x equals 0, y equals 0, or z equals 0 independently. Okay? So for all my critical values, the only ones that are going to have a Hessian is the singular point 2, 2, 2. Okay? So the Hessian of gamma at 2, 2, 2. I suppose I should probably do it this way. Like that. Is going to be equal to the matrix negative 1/2, 0, 0, 0, negative 1/2, 0, 0, 0, negative 1/2, like so. Okay, so let's go through the list. D1 is going to be the top corner here, right? fxx. That's negative 1/2. D2 is going to be the determinant of these top 4 right here, right? I'm going to be splitting it down this way like this, just like D1 is here. Okay, so I'm doing the determinant of this now. That's going to be 1/4 minus 0, so 1/4. And then the determinant of this guy right here. Anytime you have just a main diagonal, the determinant is the multiplication of the main diagonal. And that's because when you do the pieces, you can see the other, like I'll do this component with a determinant, right? And then I'll do times 0 for the next ones. So it's just going to zero out. Except for this, I'm going to multiply the main diagonal. It's going to give me negative 1/8. Okay? So go back through and look at the listing of the categories. Remember, when we have a negative, a positive, and a negative, it had to be positive D2, right, for there to be an extreme value. But when D1 and D3 are both negative, then I'm getting a relative maximum. Could be a global maximum. Man, I'll never know. This is a 3-variable function. We're not going to be able to graph it in the 4-dimensional space, but we are able to identify the point 2, 2, 2 in the domain as when if I were to actually plug in, find gamma of 2, 2, 2, that's going to be a maximum value, at least relatively, maybe globally. Okay? So I hope this process has helped you understand how to find and classify the critical values to find the extrema of a multivariable function. Stay tuned next lecture where we apply this with some actual word problems, some modeling, some optimization problems.